Section 4.1, exponential functions. An exponential function is of the form f of x equals a to the x, where your a has to be greater than 0 and a cannot equal 1. Some examples are f of x equals 2 to the x, or 1/2 to the x, or e to the x. Those are all examples of exponential functions. We're going to talk about two types of exponential functions. The first one is exponential growth. That is when your a is greater than 1. So as you can see here, we're going to use the function f of x equals 2 to the x, okay? Or y equals 2 to the x for our example. Now, what we did is we went and picked some x values and plugged them in, and you can see when we put -4 in, we get 1/16, -3, we get 1/8, and so on. And it creates this graph, which represents exponential growth. So let's talk about some characteristics of an exponential growth graph. So domain is the x values. There are infinitely many x values that we can put in here. It doesn't have any restrictions. We don't have x in the denominator. We don't have the square root of an x, so we don't have any restrictions. So my domain is -infinity to infinity. Okay, then I'm going to actually jump down to what's called the horizontal asymptote. We talked about this previously. The horizontal asymptote is that imaginary horizontal line that the graph, never crosses. So you can see that we're talking about, in this case, the x-axis. So the horizontal asymptote is y equals 0. Okay? The the x-axis, this horizontal line right here. Now that we know what the horizontal asymptote is, that helps us to see the range a little bit better. We know that the graph doesn't go any lower than 0, and in fact, it doesn't even include 0, so we're going to use a parenthesis. The range is from 0, and the graph goes up forever to infinity. X-intercept, where does it cross the x-axis? Well, we just said that the x-axis is the horizontal asymptote, so this graph does not have an x-intercept. Now, y-intercept, notice that the graph crosses at 1, okay? So the y-intercept is 1, so 0, 1. And you can see here, when you plug 0 in, you get 1 out. So these are characteristics of an exponential growth function, okay? Again, we see that it crosses the crosses the y-axis at 1. It has a horizontal asymptote at y equals 0, and the domain is -infinity to infinity. The range is 0 to infinity. Next, we're going to talk about exponential decay, and you're going to see the relationship between the two. Here's a graph of exponential decay. You're going to have exponential decay when your a is between 0 and 1, so a decimal or a fraction, okay, between 0 and 1. And the example we're using is y equals 1/2 to the x, okay? So my a is definitely between 0 and 1. So let's talk about the characteristics of this graph. Again, the domain, what values we can plug in for x, are not restricted, so it's going to be -infinity to infinity. You can see that there's a horizontal asymptote again, okay? The horizontal asymptote hasn't changed. What's happened is our graph has just flip-flopped. It's now become decay, so it's going down. So my horizontal asymptote is still y equals 0, which means my range is still 0 to infinity, not including 0. No x-intercept. And again, my y-intercept is 1. So 0, 1. So very similar, except instead of having growth, so instead of going up from left to right, we're going down. We have exponential decay. Continue our talk about the graphs of exponential functions. I want to look at what's called the natural exponential function, where we have y equals e to the x. So just so you know, e is a number. Okay, and it is an irrational number like pi, so it goes on and on and on forever. It doesn't repeat, and it's approximately 2.718, and we know it goes on and on forever, okay, but it's approximately 2.7. So again, you can think of it as y equals 2.7 to the x. You can almost think of it like that, okay? Now, you have this button on your calculator so that you can see the graph of y equals e to the x. Again, it's called the natural exponential function. It is still just a growth function. You can see that the horizontal asymptote is still y equals 0. We still have a y-intercept of 1, okay? The domain is still negative infinity to infinity, and the range is still 0 to infinity. So it looks like every other exponential growth function. But this is one that we really kind of talk about a lot throughout this chapter. Example 1 is y equals -5 raised to the third power, an exponential function. Well, if you recall, our exponential function is of the form y equals a to the x. So this is not an exponential function for a couple reasons. One is because our exponent is an x, or it doesn't have an x in it. The other reason is that my a in this example is -5, and we know that a cannot be negative. So this one is not an exponential function for a couple reasons. In example 2, we're going to evaluate the exponential function f of x equals -2 to the 7 minus x. Okay? So this negative is out in front, so that 2 is not actually negative. I just want to point that out. So what we're going to do is we're going to plug in 3. So y equals -2 raised to the 7 minus 3 power. So that's -2 to the 7 minus 3 is 4. 2 to the 4th is 16. So my answer is -16. Again, that negative is not being raised to the 4th power. We're going to evaluate g of 4/3. So this time my function is g of x equals -2/5 raised to the 3x minus 1 power. So I'm going to go ahead and plug in 4/3. So y equals -2/5 raised to the 3 times 4/3 minus 1 power. So that's going to give me y equals negative, and again, still 2/5. And now let's simplify this exponent. 3 times 4/3, well, the 3's cancel out, so we're just left with 4 minus 1, which is 3. So really what's happening is you can look at it as y equals the opposite of 2 cubed over 5 cubed, okay? Given that cube to both pieces, and we've done that previously. So my final answer is y equals -2 cubed is 8, and 5 cubed is 125. So -8 1/25. Example 4, we're going to examine the exponential function of the form f of x equals c times a to the x. So the only difference between the exponential function we looked at the beginning of this lecture and this form is that now we have that constant c out in front of my a to the x. And we saw that in the previous examples. So here's how you start. They're giving you this point 0, 3, okay? That's my y-intercept. So let's see what happens when I plug in 0 and 3. So f of x is my y, so that's going to be 3, equals c times a raised to the x power. Well, x is 0. So that tells me that 3 is equal to c times a to the 0. Well, anything raised to the 0 power is 1. So if I solve for c, I get c equals 3. So when they give you this right here, this piece, this y-intercept, that y-intercept is always going to be your c. You don't have to show this work every time, okay? Now, once you have that piece of information, you now are given another point, and that's going to be your x and your y. So you're going to plug those in, and we're going to solve for the a. So again, my equation is y equals c times a to the x. All right, so let's plug in my y as 75. I now know that my c is 3, and I have a raised to the 2nd power. So I'm going to solve this equation, get a by itself. So I'm going to divide both sides by 3 first. So that gives me 25 is equal to, these 3's cancel out, a squared. Well, we know to get rid of a square, we take the square root of both sides. So a is going to equal, well, normally we would do the positive and the negative, but we know in an exponential function, a is not allowed to be negative. So my a is simply 5. All right, so I have my a, I have my c, and I can write my final equation. Y equals 3 times 5 to the x. Okay, and if you want to put that in parentheses, you can. So y equals 3 times 5 to the x. For example 5, we're going to describe the transformations of the exponential function f of x equals 11 to the x power. So when we look at this new function, we see a couple things. First, we see this negative out in front. All right, we see a minus 5 in the power, and then we see a plus 6. Okay, so we got to think back of what these transformations are doing. So when there is a negative outside, okay, a negative outside, that's going to reflect across the x-axis. When you are subtracting inside the function, so we're subtracting inside this original function, 11 to the x, that is going to make your graph shift either left or right. Well, when it's a minus, that means it's shifting to the right. So this is going to go right 5. And then when you're adding or subtracting on the outside, it's either going to go up or down. When it's addition, it means it's going up. So we're going up 6. So we have 3 transformations going on. We're reflecting across the x-axis, going right 5, and up 6. For example 6, we're going to start by describing the transformations of f of x equals 9 to the x. So again, we got to look and see what kind of transformations are going on. We see first this plus 2 on the inside. So inside means you're going to go left or right. When it's a positive, that means we're going to the left 2. This minus 4 is outside of the function, okay? So that's going to tell us we're going down 4. So my transformations are left 2 and down 4. So what you want to think about is, what does a normal exponential function look like? So this is 9 to the x, this is exponential growth. So normally, just kind of do a little sketch up here for you, I know that it's going to look something like this, okay, with a horizontal asymptote at y equals 0. Now, knowing that it looks like that, all right, and knowing that it normally crosses at 1, what I'm going to do is I'm going to take this y-intercept of 1, and I'm going to shift that to the left 2 and down 4. So normally I would be crossing right here at 1, all right, but I'm not. I'm going to be crossing at, instead, left 2, down 4. I'm going to be crossing right here, okay, at the point negative 2, negative 3. Now, what happens is, if you transform the graph, you're also moving the asymptote. Well, we had an asymptote normally at 0, okay, at y equals 0. Well, shifting left and right doesn't affect that. But now, this down 4 is also taking my asymptote down 4. So it was here at y equals 0. Now, it's at y equals negative 4. So I'm going to draw a little line here at negative 4. That's my asymptote, okay? So let me make it a little dotted. Whoop. Oh, didn't let me do it dotted. No worries. Okay, so then what I'm going to do is I'm going to just draw the general shape going through this new point, okay, negative 2, negative 3, and with the general shape of what an exponential growth function looks like. So my graph is going to look something like this. I've gone ahead to a new screen so we have a nicer graph. You can see that this is the graph of g of x equals 9 to the x plus 2 power minus 4. So again, you can see right here, that point that we were isolating before, negative 2, negative 3, is still on the graph. I've highlighted y equals negative 4, which is the horizontal asymptote. Okay, so here's what the graph looks like. Now let's figure out what the new domain range, y-intercept, and horizontal asymptote are? Well, I'm actually going to start with f because we already know that the horizontal asymptote shifted down 4. It was at 0. It's now y equals negative 4. Okay? Domain. Remember, domain is the x values. When you look, this graph goes forever to the left and forever to the right, and we have no restrictions right here, okay? There aren't any restrictions as to what we can plug in for x. So my domain is still negative infinity to infinity. The range. Normally, the range of your exponential function was 0 to infinity, but since my horizontal asymptote has shifted down, my range has shifted down. So my new range is everything from negative 4, not including negative 4, up to infinity. And the last piece, state the y-intercept. Well, I don't see on the graph where it's crossing the y-axis, but algebraically I can still find the y-intercept. Remember, the y-intercept is when you put 0 in for x. So that's going to give me y equals 9 raised to the 0 plus 2 power minus 4. So that's going to give me y equals 9 squared plus 4. We know 9 squared is 81. 81 plus 4 gives me 85. So my y-intercept is 0, 85. That's why I don't see it on the graph. Okay, it's way up there. For example 7, it says write the equation of the graph in the final position. So we're taking this graph, y equals 4 to the x, and we're putting the transformations into the equation. So it says we're shifted 10 units to the right. 10 units to the right is what's happening inside. All right, if it's going to the right, we know that it's going to be a minus on the inside. And 3 units up, we know that that's going to be on the outside. And in order to make the function go up, you have to add on the outside. So I'm going to write my new function. My new function is y equals 4 to the x minus 10. Okay, now I have that minus 10 on the inside, which is going to shift it to the right. And then I need this plus 3 on the outside, plus 3. So my new equation is y equals 4 raised to the x minus 10 power plus 3. Example 8. Graph g of x equals e to the x minus 4 using transformations. So I know that normally an e to the x function, which is just an exponential growth function, would look something like this, okay? It's exponential growth, and the y-intercept is normally 1, okay? So the y-intercept is 1. And I know that the horizontal asymptote is y equals 0. Now, using transformations, this minus 4 is going to take my graph and shift it down 4. So that means my horizontal asymptote is going to shift down. Okay, it was at 0, now it's at negative 4. So I'm going to just do a little highlighted line to show you. So here, negative 4 is where my new asymptote is. And then my y-intercept has to also shift down 4. So if it was at 1 and I go down 4 units, I go down 0 to negative 1 to negative 2, my new y-intercept is at negative 3. All right, and then I just go ahead and draw the general shape of my graph. Again, my asymptote is negative 4, so I don't want to cross negative 4. So my graph is going to look something like that. Screen, so I have a much nicer graph, but it's still the graph of y equals e to the x minus 4. So we graphed using transformations, and we talked about the new horizontal asymptote and the new y-intercept. So the horizontal asymptote we know went down 4, so the new horizontal asymptote is y equals negative 4. Remember, an asymptote is the equation of a line. Okay, and the new y-intercept, well, you can clearly see right here it's crossing at negative 3. So my y-intercept is 0, negative 3. For example 9, we have the function g of x equals e to the x plus 3 power. Now we know that e to the x is an exponential growth function. So what is this plus 3 doing? Okay, well this plus 3 is inside the power, and we know that if we're adding on the inside, that's going to shift my graph to the left. So this graph is going to the left 3. Now it doesn't ask us to graph it, but we know that visually graphing it will help us find the horizontal asymptote and the y-intercept. So normally e to the x looks like this. If we shift it simply to the left 3, okay, I know that my graph is still going to look similar, just shifted to the left 3 units. So what does that do to my horizontal asymptote? Well, horizontally, I made the shift, so my horizontal asymptote remains the same. It's still y equals 0. Now, the y-intercept, you can see, definitely changed. We want to do that algebraically. So the y-intercept, remember, you're going to make x 0. So y equals e to the 0 plus 3. So my y-intercept is e to the third. Just simply leave it as e cubed instead of doing it in the calculator and giving me a decimal. So we can write that as 0, comma, e to the third power is my y-intercept. Example 10. This time we're given the function g of x equals e to the negative x plus 5. Part A says describe the transformations. Well, we have a negative inside the function. A negative inside the function is going to reflect the graph across the y-axis. And then the plus 5 on the outside is going to take my graph and shift it up 5. All right, and again, to help us see what's going on, it's nice to make a little sketch. So first, we know originally e to the x looks something like this. If I reflect it across the y-axis, let's do that first, okay, that now gives me a function that looks like this. Okay, I had exponential growth. By reflecting it across the y-axis, I now have an exponential decay. All right, then plus 5 is going to take that graph that I just drew and shift it up 5 units. Okay, so it's going to be something like this. So let's think about what's happening to the horizontal asymptote. Originally, we know the horizontal asymptote was y equals 0. When I do a reflection across the y-axis, the horizontal asymptote doesn't change. It's still y equals 0. Then when I shift the graph up 5 units, I have changed the horizontal asymptote to y equals 5. Now we know that the y-intercept has changed as well. It's gone up. So algebraically, let's figure that out. So y equals e to the negative, I'm going to plug 0 in for x, plus 5. Well, negative 0 is just 0. So this gives me e to the 0 is 1. 1 plus 5 is 6. So my new y-intercept is 6. So I have 0, comma, 6. Notice this should have been actually example 10. So go ahead and change that to 10. Next, we're going to look at applications of exponential functions. And application of exponential functions comes in play with money. Okay, so compound interest. We have a formula, A equals P times 1 plus R over N to the NT. You will be given that formula on the exam. You do need to know what each variable stands for, though. A is the future value, or the later amount. P is the principal value, or the original amount. R is your interest rate. Remember, rate has to be as in decimal form. N is the number of times it's compounded per year, and they're gonna give us keywords in the problem like quarterly, annually, semi-annually. And T is the number of years. We also have a compound continuous interest formula, which is A equals PE to the RT, and you've probably seen that before. That one you will have to memorize. So we're going to look at examples of just compound interest and continuous compound interest. 11. Find the future value if $5,250 is invested at 8% compounded quarterly for 10 years. Then find the amount of interest earned. So let's look at our formula. We have A, we have P, we have R, we have N, and we have T. So let's list out what we know and what we don't know. It says find the future value. So that means we do not know what A is. That's what we're looking for. If $5,250 is invested, so that's my P, 5,250, at 8%. 8% as a decimal is 0.08. All right? It says compounded quarterly. Quarterly means 4 times a year. So my N is going to be 4. And my T is 10. So now it's just a matter of plugging everything in and then calculating it correctly in my calculator. So that's going to give me A equals 5,250 times 1 plus 0.08 divided by 4 raised to the 4 times 10 power. So I'm going to write that as 40. Okay? 4 times 10. That's where that's coming from. Whoop. My pen doesn't want to work. There we go, 4 times 10. So now you can just simply plug that into your calculator. You should be able to type it straight across. Okay, make sure you have 40 in as the exponent and see what that comes out to. That gives me A equals $11,592.21. So that's the first part. It says find the future value. That is the future value. If you were to invest $5,250 at 8% quarterly for 10 years, you would have $11,592.21 at the end. Now the second part of this question says, then find the amount of interest earned. How much money did we earn by investing that $5,250? To figure that out, you're going to take the $11,592.21. You're going to subtract what you initially invested, $5,250. And what's left is how much interest you earned, which is $6,342.21. So there were two parts to this. How much, or what is the future value, and then how much interest was earned. Example 12. How much should a mother invest at the time her son is born in order to provide him with $50,000 at the age of 21 with an interest rate of 6% compounded semi-annually? So again, I like to list out my variables, A, P, R, N, and T, and let's see what we know. It says, how much should a mother invest? We don't know how much she should invest, so that's what we're looking for. We're actually looking for the P. In order to provide him with $50,000. So that is my A. That's how much I want to have. By the age of 21, so that's 21 years, that's my T. Interest rate is 6%, so my R is 0.06. And compounded semi-annually. Semi-annually means twice a year, so my N is 2. Now, I'm going to go ahead and plug those into my formula. So that's going to give me 50,000 equals P times 1 plus 0.06, if I can get it to right, 0.06, divided by 2, raised to the 2 times 21 power, which is 42. So now to do this in your calculator, what you want to do is you want to calculate this part first. 1 plus 0.06 divided by 2 raised to the 42nd power. Do that and you're going to get a decimal. Then you're going to take 50,000 and you're going to divide by that decimal you get in the calculator. And that's how we're going to solve for P. So again, take this 1 plus 0.06 divided by 2. So I'm going to do that real quick. 1 plus 0.06 divided by 2. And I'm going to raise that to the 42nd power. And that gives me a decimal of 3.460695,894. So now do 50,000 divided by that decimal. And that leaves us with $14,447.96. So this set of parents has to invest over $14,000 in order for their son to have $50,000 by the age of 21. Example 13. Find the future value if $8,000 is invested at 6.5% compounded continuously for 7 years. When you see that keyword continuously, you know you're going to be using A equals PE to the RT. So again, I'm going to go over here. I'm going to list out my variables, A, P, R, and T. My A is how much I am going to have at the end, and it says find the future value, so I don't know that. P is $8,000 that I'm investing. My rate is 6.5%, so that as a decimal is 0.065. And T is 7. So I'm going to go ahead and plug that all in. A equals 8,000 e to the 0.065 times 7. You can type this straight into your calculator. 8,000 e to the 0.065 times 7. You're going to have to find the button on your calculator that does e raised to a power. If you're not sure, I can show you in class. But when you go ahead and calculate that in your calculator, you're going to get $12,609.39.